We will decide which one empties first, and prove it with math. Here is the visual setup. On the left, tank X has a small bottom and a large top. On the right, tank Y has a large bottom and a small top. Both tanks have the same small outlet at the very bottom. We start from Torricelli's law, which comes from Bernoulli, ignoring losses. The exit speed V equals the square root of 2gh, where h is the water height above the hole. The volume flow rate is area times speed. So Q equals a times the square root of 2gh, where a is the outlet area. Now relate this to how the water level drops. Let capital A of h be the cross-sectional area at height h. A small drop, dh, corresponds to volume A of h times dh. Volume rate change equals minus Q. So A of h times dh by dt equals minus a times the square root of 2gh. We can rearrange and integrate from the full height capital H down to 0 to get the emptying time. The time equals 1 over a times the square root of 2g times the integral from 0 to capital H of A of h over square root of h dh. This shows shape matters because A of h appears inside the integral. Each tank is a truncated cone, also called a conical frustum. With straight walls we have similar triangles, so the radius varies linearly with height. R of h equals r sub 0 plus the slope, r1 minus r0 over h times h. Then the cross-sectional area is pi times r of h squared. A of h equals pi times r of h squared. Plugging into the integral and simplifying gives a clean closed form for the emptying time of a frustum. T equals pi times square root of h, divided by a times square root of 2g, times a bracket with 3 terms, 2 r0 squared, plus 4/3 r0 times the difference r1 minus r0, plus 2/5 times the difference squared. Both tanks hold 1 cubic meter. The volume of a frustum is pi h over 3, times r0 squared plus r0 r1 plus r1 squared. We choose h equals 1 meter, and r0 equals 0.25 meters. We solve for r1, so the volume equals 1 cubic meter. The outlet diameter is 2 centimeters, so radius is 0.01 meters, and area equals pi times radius squared. Equals 3.14 times 10 to the minus 4 square meters. We also take g equals 9.81 meters per second squared, and h equals 1 meter. Now compute the times. For tank X, r0 is 0.25, and r1 is 0.828. T sub x equals pi over root 2g, times the bracket 2 times 0.25 squared, plus 4/3 times 0.25 times 0.828 minus 0.25, plus 2/5 times the difference squared. Numerically, T sub x is about 1019 seconds, about 17 minutes. For tank Y we swap r0, and r1, T sub y is about 1956 seconds, about 32.6 minutes. Why does tank X empty faster? Look at the integral for time. It has a of h divided by square root of h. The factor 1 over square root of h is very large near the bottom when h is small. So the geometry near the bottom matters most. Tank X has a small cross-section at the bottom, so there is less volume where the weighting is strongest. Tank Y has a large bottom, so there is more volume where the weighting is strongest. That is why tank X empties faster. Let us visualize the draining qualitatively. We will let the water levels drop side by side. Tank X empties sooner than tank Y, consistent with our calculations. Final answer. Tank X empties first. With our chosen numbers, tank X takes about 17 minutes, and tank Y takes about 33 minutes. Even with the same total volume and the same outlet, shape matters because the bottom is weighted more strongly in the time integral.